This video is going to help us transform functions using mapping notation. So I'm going to give you just any generic function, and we're going to call it y equals f at x. And that can represent any function. And when we say a transformation, then what we do is we change this function. It keeps its general shape, but we change it either by moving it left, right, up, down, by stretching it or compressing it. And the new function can have changes in it. So we're going to keep the old function, which is our f at x function, like this. And I'm just going to change pen colors so you can see all the different places we can add changes to the function. If we put something at the front of a function, it's called the a value, and it's going to cause a stretch or a compress to that function. If we put something in front of the x value of the function, it's called our k value. It will also cause a stretch or compress, but this time along the x-axis. A d value that I put after the x, then that's going to cause a shift to the left or right. And if I add a c value to the end of the function, let's do that in black, then that's going to cause my function to move up or down. Okay? So stretch or compress along the x-axis, moving left or right, and moving up or down. So whenever we get a function, we have to decide a couple of things. We have to determine, first of all, 1, what is the parent function? 2, what types of transformations has been added to the parent function? So what a, k, d, or c? And then 3, what is the new mapping notation? Okay, so all of our basic functions then are going to have points on it, x, y points that exist in the original function. And they are going to be transformed. They're going to be changed into new points based on mapping notation. And mapping notation always works in the same way. You take all your x values from your original function, divide them by whatever the k was, and then you subtract whatever the d value was, and that's going to be all your new x values. And then you take all your y values, multiply them by a, and then add c. So notice that all the x values are having the opposite function performed on it. So even though the k is multiplying the x here, it's going to be divided by k, and the d value, if it's positive, is going to become a negative. The y values always have it kind of at face value. So you multiply by a and add c. Okay, so let's do an example to see how this actually works. So let's say, for example, we're given the function f at x is equal to 3, absolute value sign, 2x plus 4, close the absolute value sign, minus 1. We have 3 things that we need to do, like I said earlier. First of all, identify what the parent function is. So we have to look at some clues in the function that tell us what the parent function is. And we can see that because we've got these absolute value signs there, that the parent function is going to be the function f at x is equal to the absolute value of x. The reason we need to do that is this gives us some of our original points that we're going to use when we get into our mapping function. Okay, the next thing I need to do is I need to identify all of the spots where, we have any new things added from the original function. So the original function is just the absolute value signs and x. Absolute value signs and the x. So let's mark those on the given function. There. Anything that's not highlighted in green right now, those are different transformations that are going to occur. And so we have to identify what transformations those are. So you can see that here I've got an A value. Here I've got a K value. Here I've got a D value, and here I've got a C value. Now we need to stop for a second because there's a little bit of a trick in here. There's always a rule when we're using mapping notation that we need to factor out the K value. Because what we think is going to be our D value is not. So this is always going to be our first step. Sometimes it'll already be factored out, but in this case it's not. So our first step is going to be this. So our function with the factored out K value is going to still be 3, absolute value sign, factor the K value out of this part of the function in here, and you're going to be left with x plus 2. Absolute value sign minus 1. And notice the difference in the D value. So what looks like it was going to move 4 to the left is actually saying it's only going to move 2 to the left. Okay, let's talk about these transformations we have going on. So we can see that we have an A value that equals 3. And what that means is that this is going to be a stretch by 3 on all of my y values. So all of my y values are going to be stretched by 3. Okay. Next in line is I have this 2 right here. And so that means I have a K value that equals 2. So that means that all of my x values are going to be compressed by 1/2. Okay, now I have this other 2 here. This is my D value. My D value also equals 2. And that means that the whole function is going to move left 2. So again, like I said, the K and the D, they act on the x, and they do the opposite of what it looks like they're doing. So this is multiplying by 2. We're actually going to be compressing it by 1/2. And this looks like it's plus 2. We're actually going to be moving it left 2. Finally, we have this minus 1 at the end. That's going to be our C value. Our C value is at minus 1, and this tells us we're going to move down 1. All right? So the K and the D, they act on the x values. The A and the C, they act on the y values. All right, so now we've got down pat what transformations are going to occur. The next thing we have to do is we have to set up our mapping notation. And I'm going to set up all of my original x, y values, and these come from the parent function. F at x is equal to the absolute value of x. And I want to see what they're going to become when I put on all these different transformations. So it's like reading in code. And if you remember, mapping notation is always in the form x divided by k minus d, ay plus c. So I'm going to take all my x values, I'm going to divide it by the k value, which in this case is 2, and I'm going to subtract the d value. So it's going to be minus 2. And all of my y values are going to multiply by 3, and then I'm going to subtract 1. So the next thing I need to do is I need to get a few values here for mapping notation so that I know what they're going to become in this new transformation. And in order to do that, you need to know how to graph each one of your parent functions. So I usually like to choose some values, some values below 0, -2, -1, 0, 1, and 2, and some of them above, and see what the corresponding y values are from the parent function. So if I put -2, which is my x value, into the absolute value bracket, it's going to come out as a positive 2. If I put -1 in, it's going to come out as a positive 1. 0 in, of course, is going to come out as a 0. 1 is going to come out as a 1, and 2 is going to come out as a 2. And that's my absolute value, my basic graph. If you remember, it looks like this. That's my parent function. I want to see what happens when I add all these crazy transformations to it. So what I'm going to do is I'm going to take all my this x value, -2, and plug it into this formula I've got here. And it says take your -2, divide it by 2, it's giving me -1, subtract 2, which is going to give me -3. So what used to be at -2 on my x is now going to turn into a -3. And then I'm going to take the y value, which is +2, plop it in here for this y, and then just do the math. 3 times 2 is 6, minus 1 is 5. So what used to be the point -2, +2, which would have been about here, is now going to become the point -3, +5. So it's going to be transformed into about that area, okay? And then we're going to repeat it for all the other points. Now it's going to be a lot easier to graph. Okay, whereas the original function looks like this black function I've drawn on here, the new function is going to look like this. This is going to be my vertex at -2, -1. So -2 down to -1. And then I'm going to graph each one of these points. So at -3, +5, it's going to be about there. -2.5, +2, -2, -1, which I've already graphed there, -1.5, +2, which is here, and -1, +5, which is there. And so if I connect it, it goes through all those points, it's going to look like this. And there's my transformed function. So let's see if it matches what I originally thought. Have I stretched the function by 3? Am I rising at a quicker rate? Yes, I've done that. Is my function compressed horizontally by 1/2? That is squished in about half the size that it used to be. Looks like it's along those lines. Have I moved the vertex of my function to the left 2? 1, 2, I sure have. And have I moved it down 1? Yes. So I know that this new transformed function matches the transformations that were in the equation. Okay, so here's example number 2. We've been given this function, and again, we have to go back and determine the 3 things we need to know. We need to determine, first of all, what is my parent function? And so again, I look back into the function and I see if there's any clues, and of course the square root sign is a clue. So I know that my parent function is going to be the function f at x is equal to the square root of x. To factor first. Okay, and in this case again, I need to factor out that k value. So my function rewritten is going to be the square root of 1/2 factored in front of x plus, now be careful with the math here, if I'm factoring out a 1/2, it's like taking 1 and dividing it by 1/2. Dividing by 1/2 is the same as multiplying by 2. So it becomes x plus 2 in my bracket underneath the square root sign, and then this -3 gets kicked out at the end. I want to make sure I'm choosing nice whole values that actually work for that parent function. So in this case, 0, 0 works, 1, 1 works, 4, 2 works. So now all of these old values have become this using mapping notation. And let's just do a quick sketch of what this is going to look like, kind of in that direction, like that. Okay, speaking of which, let's talk about what restrictions there are on x. I know that everything underneath the square root sign here has to be greater than 0, or is equal to or greater than 0. So I know that 1/2 times x plus 2 has to be greater than or equal to 0. So what values does that work out for x? Well, if I divide both sides by 1/2 of this equation, I'll be just left with x plus 2 is greater than or equals 0. And then I'm going to subtract 2 on both sides, and x is going to be greater than or equal to -2. That can be equal to -2 all the way up to positive infinity.